Waiting for some more viewers before I begin. Man, people are slow to join today. All right. I'm not going to wait for these people. We're going to get started, even though there's only 12 viewers. All right. So, today we are going to talk about waves. Waves. This is a new topic, and it's pretty closely related to simple harmonic motion, but it's not quite the same. So a wave is a disturbance of a medium which carries, or that carries, energy from place to place. All right. When I say a medium, what I mean is the thing a wave travels through. Good morning. For example, a sound wave, or sound waves that we most often encounter, are traveling through air as the medium. In the case of, but sound waves can also travel through different mediums. They can travel through the Earth's crust. They can travel through water. You can have mediums like a vibrating string is a medium for a wave, like in a stringed musical instrument. You can have an interface between two different things be a medium. So, for example, if you go to the beach and you watch the waves, the medium is the interface between the air and the surface of the water. Okay? So the medium is the thing that the wave is traveling through. So the thing that is carrying that energy from place to place. So what I want to imagine is you are in the ocean swimming. Okay? So here's an ocean wave. Okay? And this ocean wave is traveling to the right. So this is a traveling wave over the surface of the ocean. Okay? And you're swimming in the ocean. So you are right here, treading water. So this is you. Your friend is also in the ocean with you, because if you're swimming in the ocean, you should probably do it in pairs. You don't want to be swimming out there by yourself. You could drown. Buddy system, everybody. Buddy system. So here's your friend. Okay. Now, what if we were to do a position time graph for you and for your friend as this wave goes by? All right. So if we were to do that, so first of all, as the wave, if you're in the near the shore, waves will actually move you around from side to side. But if you're just in the deep ocean, then the waves are actually just going to cause you to bob up and down. Okay? So they don't really push you from side to side. They just cause you to bob up and down. So if we were to look at a graph of your height, your elevation versus time, okay, it would look like this. Okay? So you are undergoing simple harmonic motion. So basically, when a wave passes through, the medium undergoes SHM. So that is why we learn about simple harmonic motion first, okay? So you are going to bob up and down with the wave. And so we define amplitude and period exactly like we did for simple harmonic motion. So the amplitude of a wave is the distance, is the maximum displacement from equilibrium. Equilibrium being the undisturbed surface of the water. So this would be equilibrium. And then the period is going to be the time between the time it takes for the wave to lower you down and then raise you back up again. Okay. So this is the graph of your position as a function of time. But now we could see what is the position versus time graph of your friend. And what we notice here is that because you and your friend are at different locations, you're both going to be bobbing up and down. But see how you're up here at the crest of the wave, crest being the highest point of the wave. So this is called the crest. And then the lowest part of the wave is called the trough. So when you are on a crest, your friend is in a trough. Okay? So basically, when you're at the highest point in your simple harmonic motion, your friend is going to be at the lowest point. So your friend's position time graph is going to have the exact same period and the exact same amplitude, but it's going to be out of sync, because whenever you are low, your friend is high, and whenever you are high, your friend is low. Okay? So when a wave passes through the medium does simple harmonic motion, but different parts, but the SHM is out of sync for different parts of the medium. Okay, so we have So when a wave is passing through a medium, all the different parts of the medium are undergoing simple harmonic motion, but they are out of sync. So they are arriving at their highest point at different times. Okay? So that is an important point. Now this is a traveling wave, and so when I say a traveling wave, well, if we looked at the wave at a later time, this peak is going to have moved. So at a later time, the wave is now going to look like this. Okay, the peak has gone from here to here. So we could look at what is the, and we can see that now this person would be at this location. So they're actually going to move up to that location. And now the wave height is down here. So this person will move down to that location. At any rate, we could look at the horizontal displacement of the crest of the wave. And so we could follow it. So the wave has a speed, which is basically the speed of a crest. So there's such a thing as the wave speed, which is denoted by v, just like any other speed, which is the speed of a fixed part of the wave. So we can use any reference point. So we could use the crest and track the crest and see how fast the crest is moving. Or equally, we could look at the trough and see how fast the trough is moving. Or we could just look at any random point, and as long as we keep it consistent, we can track how fast that point is moving. The speed of a wave is determined by the medium. Okay? So the medium of a wave tells you how fast the wave is going to be going. So for example, if I have a sound wave in water, or sorry, in air, so air being the medium tells me what the speed is going to be, and it's going to be around 340 meters per second. Now, why do I say around 340 meters per second? Well, because the speed of sound depends on the properties of the air at any given moment. So, in particular, the speed of sound depends on temperature. Sound travels faster in higher temperatures. Okay. The speed of sound also depends on humidity, how much water is in the air, because that. So when sound is passing through air, remember it's undergoing simple harmonic motion. The air is undergoing simple harmonic motion, and we know that the period of simple harmonic motion depends on the mass, like in a mass spring system. So if you put more water in the air, it's going to change the mass of the air, which changes how quickly it undergoes simple harmonic motion. So it depends on the properties of the air, but it's usually around 340 meters per second. The speed of sound in water is actually much higher. So it's around 1,500 meters per second. Okay? 1,500 meters per second is the speed of sound in water. So it travels much faster through water. And again, the speed of a wave in a particular medium depends on the properties of that medium. So water, now the key fact that water, or the key property that water has that makes the wave travel so much faster, is that water is incompressible or is really difficult to compress. And so that ends up being the reason why sound travels so much faster through water. Sound can also travel through solids. You know, if you put your head down to concrete and you have someone knock their hand or take a piece of metal and hit it on the concrete, then you are going to you're going to be able to hear the sound through the concrete. And so the speed of sound through a solid is going to be 2,000 meters per second plus. So it goes really fast through solids. And that's, again, because solids are not very compressible. There's a great question in the chat, which is, would elevation affect the speed of sound? Yes. Because, and the main reason, there's going to be two reasons for that. One reason is that as you go up into the atmosphere, you get a temperature change. And the other reason is that you get a density change of the air. So the air is less dense the higher the altitude is. So both of those things are going to conspire to change the speed of sound. I'm not positive, but increasing the density of the air is going to make the sound travel slower, but increasing the temperature is going to make it travel faster. So as we go up in altitude, the air is going to become less dense, which would tend to make the sound wave travel faster. But then as we go upward, the air is also going to get cooler, which is going to make the sound travel slower. So we have two competing effects, and I'm not sure which one wins out, but it's probably going to change from 340 meters per second. All right. So we can make two graphs when we're talking about waves, all right? So we could make a displacement versus, so this is displacement versus time graph, okay? And so when we make a displacement versus time graph, this is the displacement of a particular part of the medium. Okay? Just like when we made this graph here, we looked at the displacement of u versus time, and then we looked at the displacement of a friend versus time. So because you guys were at different parts of the medium, so you had a different displacement time graphs. So when we draw a displacement time graph, we are only looking at a single part of the medium, okay? And so it's going to look like, like displacement time graphs do. So, maybe it looks like this. All right. And so from that graph, we can determine the amplitude and we can determine the period. All right. Another graph we could draw is a displacement versus position graph. Okay, so a displacement versus position is like a cross section of the wave. So it's going to look like this graph right here, because here on the horizontal axis, we don't have time. We have different points in the medium. Okay, and so this graph is going to have a different look to it. So they're both going to look like simple harmonic motion, but notice how this simple harmonic motion, the waves are spaced differently because we have a different horizontal axis. Here it's time, here it's position, okay? We can get the amplitude from either graph, so this would also be the amplitude. But this distance right here is not the time between crests, it is the space between crests. And so that is called the wavelength, which is denoted by the Greek letter lambda. Okay? So the wavelength lambda is the distance between crests of the wave. Okay? Distance between crests of the wave. So wavelength is going to be measured in meters, whereas the period is, of course, going to be measured in seconds. Okay? Now, just like this graph is the displacement of a particular part of the medium versus time, this graph represents the displacement of the medium at a particular moment in time. Okay? Because we know that waves don't like to stay in place. They need to move. Okay? So just like here, at a particular moment the wave looks like this, but at a later moment the wave has moved from point A to point B. So now it's going to be, its peaks and troughs are going to be at different locations. Okay? So yes, there's a wavelength lambda. For this graph, there is also something called the frequency, which is denoted by F. And the frequency is equal to 1 over the period. And the frequency is equal to the number of wave vibrations per second. Okay? And so 1 vibration per second, 2 vibrations per second. Oftentimes waves can vibrate really fast, so thousands of times per second, even millions of times per second. So waves can vibrate really, really fast. Depends on the type of wave. So sound waves are oftentimes going to vibrate in the thousands of times per second, whereas light waves can vibrate really, really, really fast at, millions of vibrations per second, or even billions of vibrations per second. So the unit of frequency is called the hertz, which is abbreviated Hz, and 1 hertz is 1 vibration per second. Okay, so 1 hertz would be 1 1000, 2 1000, 3 1000, 4 1000. 2 hertz, 2 vibrations per second. 1, 2, 3, 4. 3 hertz, 3 vibrations per second. 1, 2, 3, 4. 5 hertz, 5 vibrations per second. 1, 2, 3, 4, etc. I can't do millions of vibrations per second. The frequency is typically determined by the source of the wave. So remember, the speed of a wave is determined by what is the wave traveling through. But the frequency of the wave is determined by what is creating it. So if I'm creating a water wave by splashing, how often I splash the water and how big and I should say the amplitude is also determined by the source of the wave. So if I want to control the amplitude of a water wave, I make big splashes. Okay? If I want a small amplitude, I make small splashes. If I want to make a wave with a high frequency, then I splash the water really quickly. Okay? Similar thing with a slinky, right? If you create a wave on a slinky, it's too... Oh man, I don't have a slinky here. If you have a slinky and you vibrate the slinky really fast, you're going to create a high frequency wave that goes back and forth along the slinky. If you make really gigantic vibrations, you are going to make large amplitude waves on the slinky. Musical instruments. The musical instrument is the source of the wave. The air is the medium of the wave. So the air is going to be what's determining the speed of that wave, but how you play the instrument determines the frequency of that wave and the amplitude. Okay? All right. So, just some reminders here. You can get the period of a wave and therefore its frequency, because the frequency is related to the period by a formula, from the displacement versus time graph. Okay, you cannot get it from the displacement versus position graph. You can only get the period from the displacement versus time graph because it has time on the horizontal axis. You can get the wavelength, lambda, this is the Greek letter lambda, from the displacement position graph, because the wavelength is the space between peaks of the wave. Okay? You can get the amplitude from either graph. Okay? So then that leads to the question, can you calculate the velocity of the wave? What is the wave speed? And the answer is yes. So there is an equation that relates the wave speed to the frequency and the wavelength, and it is v equals lambda f. So we have two equations today. We have v equals lambda f, and then we have frequency is 1 over the period. So those are our two equations for today. So again, this is the wave speed, which is determined by the medium itself. there is the wave frequency, which is typically determined by the source of the wave. And then there is the wavelength, which you can then calculate from that equation. Okay, you might have seen this equation in your chemistry class. In chemistry, you usually talk about this equation in terms of light waves. The speed of a light wave is special, and so it has its own variable, which is called c. And then frequency in chemistry is oftentimes the Greek letter nu. So type it in the chat if you've seen that from chemistry. I think it probably depends on your teacher, because different teachers go into that in different levels of depth. So we're going to do a little example. So I'm going to have two graphs. I'm going to have a displacement versus position. Notice how now I'm talking about a specific wave, and so I'm putting units on the axes. So maybe this wave looks like this. So this is going to be 10, 20, 30, 40, 50, 60, 70, etc. Okay. Very long wavelength for this wave. Typically, what happens, you could see wavelengths like this for tsunamis. Tsunamis have very long wavelengths. And then we have a displacement versus time graph. Again, putting units on the axes because I'm talking about a specific wave. Six, 8, 10. Okay, so now we have two graphs. I see a question in the chat. Would it still be frequency? I'm not sure I understand the question. Okay, so amplitude. I can get the amplitude from either graph. Okay, so the amplitude, if I go up and I figure out how far from the center line, I can see it goes about 3 meters. And similarly, if I go up here, I can see that that is also 3 meters. So these two graphs must give the same amplitude. If they don't, then something is wrong. So the amplitude is 3 meters. All right. Now we want to calculate the period. The period is the time between vibrations. So I can't use this position graph. I have to go to the time graph. And I can see that the vibration starts at 0 and it ends at about 10 seconds. So that means that the period is 10 seconds. And once you have the, oh, okay. Would it still be frequency for the chemistry Greek letter? Yes. So sometimes different textbooks or different fields use different variables for the same thing. Okay, so from the period, we can actually get the frequency. The frequency is 1 over the period, so that's going to be 1 over 10, which is 0.1 hertz. So the frequency is 0.1 hertz. The wavelength I would determine from the position graph. So here I have position, and it's the length of an entire wave. So an entire wave goes down and then it goes up. So that distance right there is one wavelength, and I can see that there's 60, and it's in between 60 and 70, so I'll call it 65 meters is the wavelength. You could also do the difference between troughs. So maybe this trough is at 15 and this trough is at 80, so you have 65 meters. I didn't draw this perfectly symmetrical, so depending on if I did this distance, it might be different from that distance just because I failed at drawing it. But it's about 65 meters. So now we can calculate the wave speed. V equals lambda f. So the wavelength is 65. The frequency is 0.1. And so we get a wave speed of 6.5 meters per second. All right, pretty straightforward. Let's do another example. Let's suppose that you are floating in the ocean. Okay, here's the ocean floor. Here's the surface of the ocean. You're floating. And you can actually hear sound through the water. Okay? If you stick your head in the bathtub and you go, you can hear it. So let's say that the water at this particular spot is 50 meters deep. So you're way out in the ocean. So you create a sound wave, okay? And the sound wave that you create has a frequency of 800 hertz, okay? Now what's going to happen is the sound is going to travel down, and it's going to hit the ocean floor, and it's going to bounce back at you. This is how sonar works. And this is what an echo is, okay? So an echo is when a wave that you create bounces off something and comes back. All right? So the first thing we could do is we could calculate the wavelength of this sound. So taking this fundamental equation and dividing both sides by frequency, we get that lambda is wave speed over frequency. The speed of the wave is determined by the medium, okay? And this is a sound wave traveling through water, so that speed is 1,500 meters per second. The frequency is determined by the source, which is the person yelling, 800 hertz. So we work that out, and we get that the wavelength is about 1.9 meters. Okay? The other thing we could calculate is the time for the echo to return. So here's the thing about waves. as long as a wave is staying in the same medium, it travels at a constant velocity. Okay? A wave travels at a constant velocity. Waves can jump between mediums. Okay? You know, if I shine a light through a window, that wave, it has to travel through the air, and then it travels through the glass in the window, and then it travels back in the air. Okay? Or if you shine a flashlight into water, it travels through the air and then into the water. So waves can jump between mediums, and when that happens, the speed will change. But if it's within the same medium, it keeps the same speed. Okay? And this wave goes through the water and then back. So it's going to travel at a constant velocity. V equals displacement over time, which is a constant. So we would not use an equation like delta x equals 1/2 at squared, because this equation represents an accelerating wave. Would represent something that's accelerating. Okay? So now we plug in numbers. We know that the speed is 1500. And here's the little trick that people often mess up on. When a wave echoes, it travels to the ocean floor and then back to you. So it covers this 50 meters twice. It goes bump, and then it comes back. So that means that the total distance traveled is not 50 meters, but it is actually 100 meters. So make sure you understand why that is 2 times what the depth of the water is, divided by time. And so we can solve for the time elapsed. We get that the time elapsed is 0.07 seconds. Okay, one last thing, and then we will go to the Zoom room. I wanted to talk about our senses. So it turns out that our ears are sound wave detectors. Okay? Our eyes are light wave detectors. All right? So light wave detector, sound wave detector. And your brain is processing those signals. It's getting signals of light waves from my eyes, signals of sound waves from my ears. So how does your brain process that information? Well, if you have a sound wave, what we perceive as volume or loudness, that is the way our brain processes amplitude. So a loud sound is one with a larger amplitude than a quiet sound. The pitch of a sound, so is it a high note or a low note? La, la. That is how your brain interprets frequency. Okay? So your brain is perceiving amplitude and frequency, but you perceive it in your senses as volume and pitch. Okay? But using science, we can actually give these numbers, numerical values. Your brain doesn't give you numerical values for these, but you just kind of know. The brightness of a light wave is how your brain interprets amplitude, and the color of light is how your brain interprets frequency. Okay, so bluer, Roy G. Biv. Okay, redder colors have a lower frequency. Bluer colors have a higher frequency. All right. So 2 out of your, excuse me, 2 out of your 5 senses are wave detectors. Another 2 of your senses, smell and taste, are basically chemical detectors, right? So you have taste buds, and a chemical touches the taste bud, and the taste bud can tell which chemical touched it. Your brain perceives that as a taste. You have olfactory receptors, which are, chemicals bump into the olfactory receptor, and it knows which chemical it was. Your nose is detecting chemicals in gases. Your mouth is basically detecting chemicals in liquids. And then your 5th sense, which is a sense of touch, is essentially a pressure sensor. So, when you push down on skin or whatever, that sends an electrical impulse to your brain, which you interpret as touch. So, our brain processes that information, but really it can boil down to physics concepts and chemistry concepts, all of those senses. All right, so that's my lesson for today, and I will see you in the Zoom room.